Muy bien, ha sido la presentación de don Enrique Escobar, quien es el consejero en Chile de Softwood Export Council. Mr. McDonald, por favor.
Great. Buenas tardes. Good evening. Thank you. So, thank you for having us. It's my first time in Chile, and I've been here for 3 days, and so far I'm really enjoying the experience. So, I'm learning every day about your construction sector and the wood industry, and I've got lots more to learn. Enrique, my good friend and colleague, was just talking about the use of Douglas fir in Chile, and today I've come to talk to you about new ways of using wood that we're exploring in the United States. And I want to give you a quick tour through the world of what we call mass timber, using new products like cross-laminated timber, actually not so new, but using them in ways where we can build bigger, taller buildings with wood safely and innovatively. So I'll start by explaining my own institute. The Tallwood Design Institute is a partnership between the College of Forestry at Oregon State University in the northwestern USA, the College of Design at the University of Oregon, and the College of Engineering. So what we're trying to do is combine architecture, structural engineering, and wood technology and science together to research and develop new solutions with wood. So we really have two purposes. The first is to grow the manufacturing base for structural wood products in Oregon and the western United States. And then secondly, to eliminate and overcome some technical challenges and perhaps some public perception challenges around using wood in new ways, or perhaps returning to old ways with a more modern system. We're investing heavily in this at Oregon State University. We are spending $70 million for 3 new buildings: a new College of Forestry building, a new structural laboratory, and some other buildings. So what is cross-laminated timber? It's been described as plywood on steroids. So taking pieces of lumber, I'm not sure if this, okay. So basically, instead of plywoods where you have veneers that you alternate this way at right angles to build strength in 2 directions, CLT employs the same technique, but using lumber. So you put sticks of lumber down, some glue, right angles, same thing again, spread some glue and right angles, and that way you build layers. You can see here 3, 5, or 7 layers thick. Sorry. So this originated in Austria, and it was a use to. The reason for this was to try to create new value for the lumber that was used in the sawmilling process. The lumber that comes off the side of the log is often a smaller dimension. It's not as useful. It's not as high value. Sometimes it's viewed as waste. And so researchers in Austria, prominently Gerhard Schickhofer and others, did a lot of research on this, testing the structural of CLT panels, and began to build buildings around 1993. And then the first cross-laminated timber manufacturer, KLH, was established in 1997. So it remains a market leader worldwide today. Today, you can see that most of the production facilities are still located in the German-speaking regions of Europe, so Austria, Germany, Switzerland, and with some production happening now in Sweden and Austria, and Sweden, Finland, and Norway. In terms of global output, Austria is responsible for more than half of global production. Germany is next, and then Italy, and then some new players are coming in: Canada, Japan, and the US is just getting started, but I think we're going to see rapid acceleration in the United States. Globally, you see a few facilities in North America, mostly in Europe, and then in Japan, there's also lots of interest. There's a factory in New Zealand, and there's one coming online in Australia shortly. This is by one of my colleagues who's surveyed CLT manufacturers and looked at the expected growth in the market. And as you can see, in 2015, when he was doing this research, we were already on a very steep upward trajectory. All right. Testing, testing. My batteries are running out. Sorry, it's late in the day. So you can see the market growth is expected to be quite rapid. And my colleague also asked manufacturers whether they were expecting to increase their output in the next 12 months, and about 1/3 of them said that they were. So we're not just talking about cross-laminated timber. There are other systems available to build larger with wood. Glulam, which you see on the left, top left, has been around since the 1960s. Sure, you're familiar with it. Then we have some new products at the bottom. The one on the left is using dowels, no glue. So it's purely a very environmentally friendly product. And we have some other solutions just emerging using LVL and using plywood. So why do we want to build bigger with wood? Well, 50% of the world today lives in cities, 50% of our population. In about 20 years, 3/4 of the world's population will live in the city. So we have rapid urbanization, and it's estimated by the UN that 3 billion people will need a new home in the next 20 years. So that is butting heads with the problem of climate change. And so when we think of climate change and the emissions from greenhouse gases, we usually think of cars and industry, but it's a fact that almost half of the greenhouse gas emissions actually come from buildings in some way. And how does that break down? So it's in two ways. The embodied energy used to create the materials to build with, and then the operational energy used to heat and light the buildings during their lifetime. Today, 30% of the greenhouse gases from buildings comes from the embodied energy, the energy used to make the materials for the building. Because our lighting is getting more efficient, our homes are getting more energy efficient, our windows are getting better, in about the next 10 years, that's going to be more like half and half. So half of the greenhouse gas emissions from buildings are going to come from embodied energy. And when we look at these charts here on the left, you see the energy required to produce wood versus steel and concrete. So you can see some very good environmental arguments for using more wood in buildings. And then the greenhouse gas emissions, wood compared to 26% less than steel, 50% less than concrete. Additionally, 50% of the weight of wood is carbon. And carbon, a cubic meter of wood stores about 1 ton of carbon. So that stores rather than emits carbon during the life of the building. And at the end of it, you can often reclaim much of the wood products and use them in its next life cycle. Economically, there are some attractive benefits too. Usually, when you build with wood, if you're building a big or a tall building, the cost of the materials is a little bit more than if you're doing a reinforced concrete building or steel building. But then you save incredibly on the labor costs, because these things can be made in prefabricated sections that go together very quickly on the job site. You also have a lighter building. The foundations can be less costly. You can build in areas with soft soils, so you can put tall buildings where they otherwise would not be possible. And then there's some other advantages. You need less trucks to bring materials to the job site. There's less waste on the job site. It's quieter. it's a more attractive workplace. So, as I mentioned, most of the, when CLT was born, it was really confined to the German-speaking area of Europe, and for a few years, 10 or 15 years, really that's where it stayed. But in 2008, there was kind of a game-changing building that came along in London, England, Murray Grove. This is a 9-story cross-laminated timber building. The elevator shafts were also made of mass timber. And this started a whole, almost like a race around the world to build bigger, taller wood buildings. Right now, the tallest wood building in the world is in Vancouver, BC, in Canada. It's 18 stories tall. There's a 24-story building that's under construction right now in Vienna. And you can see many more in this slide here. In North America, Canada got into this whole area a little bit ahead of everybody else, and in particular British Columbia on the west coast. And the reason for that was the provincial leader of BC brought in a new law that said if you want to build a building that's going to be paid for with public money in this province, you must propose a wood solution. You can also propose a concrete or steel solution, but you must develop a wood solution, or you have a good reason why not. And that really started things off. Not every building automatically became built in wood, but many did. And an important driver for that was that the following year, in 2010, the Winter Olympics were held in Vancouver. And so we had this opportunity to showcase wood on the world stage. And what was interesting after that was about 53 cities and towns around the province of British Columbia, representing over 1 million people, brought in their own bylaws, their own laws, saying, if we're going to build a library, if we are going to build a school that's going to be paid for by this city, we should have a wood solution. Another reason for their interest, for Canada's interest in this whole area of building using more wood, was the value adding. Canada wanted to add more value to, for every tree that was taken out of the forest, this is a graph showing how much dollar value was generated for every cubic meter of wood. And you can see Canada at the left-hand side. These figures are about 15 years old, but you can see in those days, Canada was just above China. The US was substantially ahead, $290 per cubic meter. And then we have Germany and Japan way up here, generating 6 times almost as much as Canada. So the idea was, don't just ship logs, don't just ship lumber, let's do more, create jobs, keep the social and the economic benefit in the country. So this is the Richmond Speed Skating Oval that was built for the Olympics, featuring glulam and dimension lumber. A few other buildings, the Wood Innovation Design Center in Prince George, the Vancouver Convention Center, the headquarters of an outdoor equipment manufacturer, a retailer, and then Brock Commons. And this one is worth spending a little bit more time on. So this is currently the tallest wood building in the world. It was completed this year. Students moved in just about this month, actually, to the campus. And it surprised the general contractor with how quickly the wood went up. The crews that were installing the wood elements actually had to slow down because the people that were coming behind to do the concrete work, the electrical, the plumbing, could not keep up. So there's a short video here that is quite a nice illustration. Might just have to go here and start it off. And you can see that the building went up at 2 floors were built every week. So it took 9 weeks for the wood structure. This, if you walk inside the building today, it doesn't look like a wood building. The wood decks are covered up with a thin layer of concrete, which helps to stop vibration, helps to keep it firm, helps to stop transfer of sound through the floors. And the wood on the walls and ceiling is covered up with gypsum board for fire protection. So it doesn't feel like a wood building, but we're sequestering, we're storing a lot of carbon, and the greenhouse gas emissions from the materials used are much, much less than if we use all concrete and steel. You can see that the elevator shafts are concrete, and they provide the lateral resistance in this case for this building. It is possible to do this with mass timber, but so far it hasn't been tried on this scale of building before. The university wanted to move students in they didn't want any delays. They had students, they had a shortage of housing on the campus, and so they really needed to get people on time. So they were a little conservative when they designed the building, so there wouldn't be any delays in getting building permits. So there was a crew of 9 people working on the timber, cross-laminated timber decks and the beams, the columns, I should say. And they were, as I say, they were installing 2 floors every week. So 1 every 2.5 days. So let's switch and talk about the United States and what's been happening recently. I'm living right now in Oregon, and Oregon has become the center, the hub within the United States for mass timber. There's a few reasons for that. There's a strong support among the state government and all levels, all of the agencies working with the state government. And that's very, very important. Oregon my colleagues say it's the best place in the world for growing trees. The climate, Douglas fir grows abundantly. It rains a lot in the winter. We have warm summers. It's perfect climate, and it's really, for that reason, it's become the leading lumber producer in the United States and the leading plywood producer in the United States. However, because of various things, some conservation changes about 20 years ago, the amount of timber that was being harvested on the federal government-owned lands has gone down. And so that's meant loss of jobs in the rural communities. And the governor sees mass timber as a way to maybe bring back some of those lost jobs into those rural communities, and actually bring back much higher value jobs than existed before in those communities. Here are some buildings in Portland, Oregon, that are currently built in mass timber. This is a architectural firm, Albina Yard. This one is just going up next year, so it already has a building permit and will be a 12-story building containing retail on the bottom, office space, and then social housing on the top floors. This one is Carbon 12. This one is nearing completion. Around the US, there are other examples. This is the T3 building in Minneapolis, currently the largest wood office building in the United States. It's not the tallest, but you can see how big it is. And then this is the University of Massachusetts at Amherst Integrated Design Building. So that's all very well. We talked about some advantages of using wood. What are the challenges? What are the barriers to using wood? Well, you can probably think straight away of things like earthquakes, fire, what happens when it rains and the wood gets wet. This way of building is quite new. There's no standardized ways of connecting the panels together. You know, that's a problem because when you have customized solutions every time, it puts the cost up. You also have building contractors who are not familiar with this way of building. And so what happens when you estimate the cost of a building that you're not familiar with creating, you put the cost up, right? You add a little bit, an extra 10, 20% in case you lose money. So these buildings are still maybe artificially expensive. And as building contractors and architects and engineers learn how to do it and learn how to overcome the technical challenges, we're seeing the costs go down. And so our institute is involved in training programs and different ways of getting research information out into the community. And we need to work across the disciplines, not just among architects, not just among engineers or builders, but across the whole spectrum to tackle these problems and these questions. So the three things we do: research, product development and testing, and training and education, as I mentioned. I'm not going to go through this long list, but we have a lot of research currently underway sponsored by our institute. And I should mention, we're maybe one of the biggest institutes in the United States doing this kind of work. But there is research going on at universities all across the country. This one is interesting and I think worth mentioning here because you're living in the area with the most seismic activity in the world, I believe. On the west coast of the United States, we also have the same issues with seismic activity. And this is a system designed in New Zealand called the Rocking Wall System, where the panel is fastened with cables that run up and down through the panel and into the concrete foundation. And then in the event of an earthquake, the panel will actually rock like this, but the cables pull it back into the center when it's finished. There's some inexpensive metal connectors connecting the panels together. When the earthquake comes, these will kind of pull apart. They'll elongate, so after the earthquake, they'll need to be replaced. But the point being, it's easier to replace these small metal parts than the whole building. It was designed in Christchurch when, after the terrible earthquake there, they had very little loss of life, fortunately, but over 1,200 buildings had to be demolished. So the city was almost bankrupt, and it led the researchers there at the University of Canterbury to develop this new system. We're also doing some testing of our own, and I think you're going to see a short video of a shake table test at University of California that we sponsored recently. This is a 2-story cross-laminated timber building with various connectors that we're testing, including the rocking wall system I just showed you. That's here. And this just happened in July, so the results are still being analyzed, but we had some very favorable data. You know, we did 10 earthquakes. We simulated 10 earthquakes on this, and actually it held up really, really well. The researchers were not expecting to be able to walk up on the building afterwards, but it was safe to do so. Another thing we're working on is, this video is going to play, hopefully, is fire testing. So fire is a huge thing. Because the cross-laminated timber and these kind of products are very, very thick, what happens in a fire is the underside exposed to the flames will char. It'll develop char, just like you'll see on a log in a campfire. The char layer will then protect the interior part of the wood. So in this test, we had, in this furnace, 1,000 degrees Celsius on the underneath. So the panel that we were testing was up above there, you can just see. So 1,000 degrees Celsius underneath. And then on top, it was barely 28 degrees Celsius. You could put your hand on it during the test. We did a 2-hour test. So this is the kind of thing you don't really believe unless you see it. And I recently saw this and took this very kind of poor quality video. I apologize. This is the kind of thing that allows the timber to be used in ways that were not possible before. Now, if you're going to give a presentation at 6 o'clock in the evening after a long day on the trade show floor, you have to show explosions. Otherwise, people are going to be sleeping. So I had to put this video in here just to wake people up a little bit. There you go. Shall I play it again? So the US Department of Defense is interested in this technology for their military bases. So they're testing it to see whether this could be resilient to a terrorist threat. The results were very good, and consequently, they built this 4-story hotel on one of their army bases in Alabama. And they're seeing this as because of the prefabrication possibilities and also the blast resilient properties of these materials, this is becoming an option for rapid deployment housing, not just for military use, but also, for example, after disasters. Like we've seen too many disasters recently in the Caribbean and the southern US. But these are the kinds of systems that could be deployed quite quickly. So I mentioned we're developing a lot of training programs for manufacturers, engineers, architects, and so on. We're also educating architects, and I just wanted to mention, it's interesting, some of these studio courses that our architect students do, they start as purely learning exercises. They're not real projects, but this one was to create a 6-story parking structure. You can see some of the students' work here using mass timber. The city of Springfield, which sponsored this work, liked it so much, they're actually building one. So this is a real project. Now this is a rendering. It's not a real photo yet, but the building is being permitted right now and will start next year. Right now, our researchers are working with the city to make sure we answer all the questions about moisture, durability, rainfall, protecting these panels from getting wet, basically. Another one is this stadium project, which is happening. Eugene, the city of Eugene, is home to Nike. So Nike is spending a lot of money sponsoring events. The US Olympic team trains there. And this is another student project to develop grandstands using mass timber. Some really nice solutions there. And what we hear was the University of Oregon, where this is, are really thinking hard about perhaps building this from wood now. Originally, their plan was to build from steel and concrete. And this is a new mass timber manufacturer who's investing $30 million to put a new facility in place in Oregon. They're using plywood veneer, making big, thick panels out of veneer, basically. And this work started at Oregon State University a couple of years ago, and the company is going on to market at the end of this year. What's in the future for this whole area? Well, I mentioned Freres Lumber, that's the company you just saw, planning to open some more plants. So currently, if you look on the map, the blue stars show you where the mass timber manufacturing facilities are, one in Oregon, one in Montana. Announcements have been made such that in the next 2 years, we can expect to see perhaps 10 plants, possibly more. This is just based on what we've heard so far. In Oregon, there are some other producers that are thinking about jumping into this whole field. So when you saw that 3% of production globally was the United States, back at the beginning of my presentation, that could really be changing 2 years from now and as we go forward. So we're really excited about this area. So thank you very much for listening, and I hope you found it interesting.